Hello people. This is a very short video on basic introduction to magnetism. Now, these are some of the demos that we would have set up in the first lesson or two for you to have a look at. So we'll just go through some of them now. Now, obviously, we don't really experience magnetic fields as humans. We're in a very weak magnetic field. We don't tend to put ourselves into strong magnetic fields. Even when we do, we don't really experience them. But there are some substances that obviously do. Things like iron, certain metals will respond to strong magnetic fields. Now, you might be familiar with our good old horseshoe magnet and our bar magnets. They are colored a certain way. There's a reason for that, and we'll look at why one side is red and one side is blue in a later lesson. Now, obviously, iron on its own, let me just get these out of the way. Iron on its own is not magnetic. And in fact, in here is my little iron filings that are in oil. They're free to move around, and there's no real interaction with the iron. However, iron is ferromagnetic, and what that means is it can magnetize itself in the presence of an external magnetic field. So if I took, this is a very strong magnet, and in fact you can notice that my compass over there is already picking it up. I'll get him out the way, thank you very much. Oh, you can stay there for fun. Pretty strong, this one is a very strong magnet, and if I place my iron at the end, like so, then it has now become magnetized. Okay, so this is an example of ferromagnetism, and as the name suggests, anything with iron in them is ferromagnetic, but there are also other metals such as cobalt and nickel that can be magnetized, so they are said to be ferromagnetic. Now, this can be explained by something called the domain theory, and the domain theory talks about regions in metals where all of the electrons are spinning in the same way. Now, in aluminium, for example, aluminium's not magnetic. Neither is my gold wedding ring, which I'm pretty sure it's gold, because the domains do not align themselves. They're locked into place. Whereas with iron, the domains are these tiny little regions where all of the electrons can align themselves. And when they do, they become magnetic themselves. So when all the electrons are aligned, they produce a magnetic field. Okay, so that's your example of domain theory. So again, over here is copper, just a piece of copper, not ferromagnetic. Neither is my aluminium. It's not going to make anything happen. Okay. Now our little oil droplets, give them a shake. Can't really get him out of there. The iron droplets. I keep saying droplets. The iron filings are suspended in oil, and they want to align themselves in the magnetic field. So if I give this iron a bit of a shake, or if I take my bar magnet, how about we take our strong magnet? Now our strong magnet is so damn strong that we can't really see a shape of the magnetic fields. We can see it's really, really strong at either end, because that's where the iron filings wish to go. Okay, we can sort of collect them all up. And if we spread them all out, I might be able to get some idea of the shape. We will need to learn how to draw the magnetic fields of bar magnets, and we can sort of encourage our iron filings to get into a certain shape. So we can see that there seems to be some kind of nice pattern going from one end of the magnet to another. Okay, more on that in a later lesson. Okay. Now, this little needle here is magnetized, and it wants to align itself in an external magnetic field. And it's trying, I'm just going to get all of these magnets out of the way. It's trying to do that, and there is the Earth's magnetic field at the moment, and it wants to, over time, it's just going to keep bloody wobbling if I don't sort of encourage it to stop. It wants to align itself in the Earth's magnetic field. Now, the Earth's magnetic field is really, really weak. More on that in lesson number 2. But it wants to point a certain way. And what early travelers did is they magnetized a compass needle. It would align itself with the Earth's magnetic field, and they painted one end red, and they called that the north-seeking magnet, because that was pointing to the north geographic pole. Okay? Now, the Earth's magnetic field is quite weak, and all I need to do is take my really strong magnet, and I'm able to influence that at quite a large distance. So when my magnet comes within, 10 centimeters, 20 centimeters, 30 centimeters, it's producing a field which is stronger than the Earth's magnetic field, and it's freaking it out a little bit. Okay, now, hello. Oh, thank you very much. So that's just a very quick demo on different types of ferromagnetic and non-ferromagnetic materials.